So now we're ready to look at what is called the fundamental theorem of calculus. Okay, and with a name like that, you know it's got to be important. So this is what finally establishes the relationship between derivatives and integrals and gives us a roadmap for how we can find an easier way to evaluate these integrals. Okay, so it's generally stated in two parts. So first we'll look at part 1. Okay, so this says if f of x is continuous over an interval AB, and the function f of x is defined by f of x equals the integral from a to x of f of t dt. Okay, so know what this is doing first. Okay, so it's defining this as a function of x. So x is our variable for the function, and then you have a function within this function, which is a variable of t. Okay, so very important what it's doing here. A is just a constant. It's just the endpoint of the interval here. Okay, so that part's not as important. Then f prime of x, so big F prime of x, is equal to little f of x over a b. Okay, so this tells us that essentially that the derivative of the integral is the inner function, meaning that these are inverse functions of each other, at least in one direction, right? And that's very important. So this tells us that this is establishing the inverse relationship between differentiation and integration. And it's setting us up for being able to find the integral of a function using what's called the antiderivative, meaning exactly what it sounds like. We kind of work backwards. We look at the function and think, okay, what function could we take the derivative of to get this function, right? So we'll work on that probably in the next video. But for now, you could just look at this, and I would encourage you, you can look at going through the proof of this. It's not too hard. Just using the definition of the derivative on this part. You need a little bit of extra things like the mean value theorem for integrals, but that's not too hard to show based on what we did in the last video anyway. Okay, so some examples first. So if we have g of x equals integral from 1 to x of 1 over t cubed plus 1 dt as an example. Okay, so the fundamental theorem of calculus tells us that g prime of x is equal to 1 over x cubed plus 1. Okay, and that's it. Okay, there's nothing else to do here. Okay, so pretty straightforward to use, at least with the simpler problems here. So let's look at part 2 first, and then we'll look at some more examples, because these will kind of help us understand more complicated examples. The second part will. So this kind of, so that one gave us kind of the relationship with of the derivative with the integral. This one kind of gives us the opposite, the relationship that the integral has with the derivative. Okay. So if f is continuous over the interval AB, and capital F of x is any antiderivative and I'll define this separately, of f of x, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. Okay, so this finally gives us a way to solve the definite integral, which is that we find this antiderivative and then we plug in the limits of integration into it. Okay. Now this antiderivative, let's define that separately. So the standard definition, there's really not much to it. It's pretty much what you would expect. A function capital F is an antiderivative of f if f prime of x equals f of x for all x in the domain of f. Okay. So this kind of gives us a way to find the antiderivative, though, is that we just think about what function, if we took the derivative of it, would give us this function. So just to look at a couple of simple examples, if f of x equals 2x, then we know that the antiderivative would be x squared, right? Now, one thing that's important to note is that the derivative of a constant is 0. So technically there could be some constant on here that we don't know about, right? So that's always something we need to keep in mind, is that there's not necessarily one antiderivative, right? Technically, x squared would be an antiderivative, x squared plus 1 is an antiderivative, x squared plus 2 is an antiderivative, etc., right? Because the derivative of all of these would be 2x. Now, for definite integrals, this isn't really an issue. It's not something that we need to think about. But when we look at integrals without limits of integration, which are called indefinite integrals, we will need to take this constant into account. Okay. For now, it's not necessarily something we need to worry about, but we will need to think about it later on. Okay. So let's go ahead and look at, I want to do a separate video where we look at some common antiderivatives and look at stuff of how to actually evaluate some of these integrals now. But first, I do want to use this to kind of demonstrate some extra stuff about the first part of the fundamental theorem of calculus, namely this derivative part. Okay. So let's look at some other functions we could have here. Okay. So let's say that we have g of x equals the integral from 0 to x squared, okay, x squared of e to the t dt. Okay. So this is a little bit different from the fundamental theorem of calculus, of course. Part 1, namely. But if we think about part 2, that tells us that this is equal basically to g of x squared minus g of 0, right? So if we think about the derivative of g of x, this is going to be g prime of x squared minus g prime of 0, right? Or really, this would actually be g of 0 prime, I should say, and g of x squared prime. The difference here being that g of 0 is a constant, right? You're just plugging some number, you're plugging 0 into this, so this is a constant. So the derivative of this is 0. So the derivative of this part we could find using the chain rule, right? It's going to be g prime of x squared times 2x, okay? g prime of x squared, that'll be just the inner function with x squared plugged into it, like the theorem of calculus, fundamental theorem of calculus suggests. So this is going to be e times to the x squared times 2x. Okay. So this allows us to, the second part allows us to solve more complicated problems of the first part. Okay. And actually, you could use the second part to show the first part rather easily, right? So you have the second part saying the integral from a to b of f of x is f of b minus f of a. So here, this tells us that this is equal to f of x minus f of a. So when you take the derivative, f of a is the derivative that is 0 because it's a constant. So you just get f prime, right? So it all kind of goes together. It's all consistent with each other here. This also shows us a way to do this if you don't have a constant as your lower bound, like we do in the statement of the fundamental theorem of calculus part 1. Okay. So if we want to find, if we let f of x equal the integral from x to x squared, or sorry, let's just do x to 2x of t cubed dt. Okay. If we want to find f prime of x here, then this is going to be f prime of, let me say, it should be f of 2x prime minus f of x prime, right? So I put the prime on the outside because of the chain rule. For the second term, it doesn't actually matter. But for this first term, it does, because we do have the chain rule in effect here. This is going to be 2 times f prime of 2x, and this is just f prime of x, right? So this is going to be 2 times 2x cubed minus x cubed. So 2x cubed, that's 8 times 2 is 16, x cubed minus x cubed. So this is going to be 15x cubed. Okay, so we can use these two parts, the two parts of the fundamental theorem of calculus plus the chain rule together to evaluate these kind of integrals. Or really, we're evaluating the derivative.